Hello students. So welcome back to the class. Today we'll start the second chapter of the NCERT, Structure of Atom. So this is theory part 1. So we've already completed our first chapter, which is some basic concepts of chemistry. Today we will see the second chapter, which is Structure of Atom. I will try to start with the fundamental things. Disclaimer: the images, text and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. In this class, our objective would be to know about the discovery of electron, the discovery of proton, and the discovery of neutron. Plus, we will see their characteristics as well. If I specify the topics, then the first would be discovery of electron, about proton, which is in the NCERT section 2.1.4. Then the section 2.1.4, which is also covering the discovery of neutron. We'll start with the Faraday's experiment. So what was the Faraday's experiment? So in 1850s, Faraday began to study the electrical discharge. Now what is electrical discharge? So here we apply a very high voltage across a vacuum tube where the air is present at a low pressure. Now these tubes are called as the cathode ray discharge tubes. Remember, so Faraday was the one which studied about this, and Thomson tried to explain the characteristics of the rays that were produced. If I try to describe cathode ray, then it is made up of glass and it contains two thin pieces of metal which are called as electrode, and they all are sealed in a vacuum tube which is known as cathode ray discharge tube. Now the gases are filled there and they are present at a very low pressure and at a very high voltage. So to describe all of this point, let us see an image. So the image would be sufficient to describe all of this. Remember that we have to supply very high voltage so that the current it starts flowing from the circuit, and it is happening due to a stream of particles which is moving in the tube from the cathode to anode, which are called as cathode rays or cathode ray particles. Now these all points can be understood with the help of this cathode ray tube. So this is the beginning only. Abhi, you don't have to worry. If you are understanding this figure, you do not need to consider about these points. Okay. So this is your whole setup. Now what is there in the setup? We have a very high voltage. Now this high voltage is flowing in the circuit, and this circuit is connected to a tube. And in this tube, we have gaseous molecules which is present at very low pressure. Low pressure means, what is the meaning of low pressure? How do we create low pressure? It's very simple. So if suppose 10 moles are present at a normal pressure, just try to take out some molecules out of that tube. You will have the gas at a low pressure due to less number of moles. What will happen if we supply a high voltage? So basically, it is seen that after supplying the high voltage, although this area is vacuum, okay, you can see it very clearly that between the cathode and the anode, which is showed by a blue and a red electrode, the area is vacuum. But you know it very well that for the conductance of electricity, we need some medium or some particle to flow, and for current it is obviously your electron. So we need the flow of electron, and for that we need a conductor. But here the space is vacuum. Okay, this space you can see, this space is vacuum, but still on supplying a high voltage, we can see a current. Now this is very strange. Why it is strange? So if you ever take a open circuit, so we are taking an open circuit, right? It is a kind of open circuit because there is an absence of connecting wire between this blue electrode and this red electrode. And if it is an open circuit, then the current wouldn't flow, but there is a flow of current. So this flow of current was the basis of the foundation, which further led to discovery of electron. Okay, so the particle or the thing which is behind this flow of current, we will see about it, what it is. But till this point, we are considering that if we are supplying a very high voltage across a vacuum tube, okay, which contains only small particles, which contains only air at low pressure, then we are able to see the current. And remember, if you take an open circuit, then you won't see a current. You never see a current for open circuit. The wires should be connected. But in this case, we are seeing a current. Any doubt in this point, in this experimental setup? And what is the strange thing that is being observed? So basically, the flow of current is a strange thing instead of keeping an open circuit. Clear? So this was the Faraday's experiment. Now later on, another scientist tried to study this current flow, whose name was J.J. Thomson. So what did Faraday do? He did a small modification in his experiment. What was that modification? So at the end of the, say, cathode ray tube, he made a small hole in the anode. He made a small hole in the anode, and the tube was coated with phosphorant material, zinc sulfide. And after this, when he tried to, say, pass the current or applied the same voltage, he observed a bright spot that was developing on the coating. Now this is the figure for it. To summarize this thing, you would see that on the blue hand side, which is our cathode, the solid wedge is present. Okay. On the right hand side, where the anode is present, anode is represented by a dashed wedge. Okay, you can see that dashes are here. Now this gap in between the dashes, they represent the hole. Okay, they are the hole through which the electron can flow. Now this electrons will hit the anode as well as the tube that is present at the back because of the space that is being present. So they will pass through this hole and hit this tube. Second thing what Faraday did, that he coated this whole tube at the backward with phosphorant material known as zinc sulfide. Now this zinc sulfide is having a very strange property that on hitting it with something which is charged or something which is excited, it starts glowing. Okay, so this glowing of your phosphorant material zinc sulfide indicated that there are some particles which are moving through this vacuum, okay, and they are responsible for the flow of current. And this is being observed with the help of this fluorescent coating, which is having a yellow color bright, okay, yellow color brightness. Any doubt till this point? Anyone who has a doubt? Okay, so I am summarizing it, so please listen it very carefully, all of you who have missed the starting part. So please remember to attend, to come at the class at the given time, right? So I don't have time to repeat it multiple times, but still this is the last time, okay? So let us see it once again. So it's a very good experiment. So maybe you won't be getting the point. So our experiment goes like this. So this is our tube. Okay. And here we are supplying a very high voltage. Okay. We are supplying a very high voltage. Suppose this is your cathode. Okay. This is your cathode. What will be the charge on cathode? Of course, it will be negative. So this is negatively charged. What about anode? So anode will be positively charged. Any doubt till this experiment? Now what we did, that we vacuumed out air out of this. So we vacuum tube. Okay, so this is vacuum tube. It is basically used to pull out the air. Yes, current will flow from negative to positive. So I think I have not shown the direction of current. Okay, I understood your point. Yes, this will be the thing. Okay, Pratik, is it now okay? Okay, yeah. So this is your diagram. Now remember, I have already told you that between this, we have some amount of gas that is present. So of course, your gas will be particle. Your gas will be particle. But you know it very well that if this space is not containing any conductor, so this is obviously not conductor. So air is not a conductor. Okay. If it is not a conductor, then what will happen? Since this whole space is vacuum, therefore no current will flow here. And if no current will flow in this region, that means this whole circuit will have no current passing through it. We are using AC current here. Okay, so high voltage current can be applied through mostly through AC. So I'm representing it with this sign. Okay. So is this clear? So if you have taken a vacuum here, there will be no flow of current, right? Means this is the expected thing. So this is expected. As this circuit is open, there will be no current. No current means, so what is, when do we call that a current is flowing? Suppose this was our circuit, okay, and this is a bulb. Now when we switch on it, the bulb will glow. That means the current is flowing, or you can say the electrons are moving from here to here. Okay, so this means your current is flowing. The normal current, the electricity which you see. But if you suppose break this circuit here, like the one which we have done it here, you break the circuit here, this bulb will stop glowing. This bulb will stop glowing. So this is the meaning of no current. Got it? Any doubt in this? Is it clear to all of you till now? Yeah. Now, this no current thing was not seen. So this was our expected thing, but it was not happening. It was seen that when we supply very high voltage, okay, when we supply very high voltage, then there is a flow of current. Okay. So our expectations were not met. And this was not met at high voltage. It means that something is present in this vacuum area. Okay. Something is present in this vacuum area which is allowing the flow of current. Yes, at a low pressure there was a flow. It will not be seen at a high pressure. We will see why it is. Why is this thing happening? So you have to keep a low pressure. Okay. Now just try to grasp the observation. What is the reason behind it? Why the current is flowing? We will see it later. Just try to grasp the observation. So the observation is, I guess it is clear to all of you. Any doubt? Abhi, Navreet? Okay. So this was the observation. It is seen that at high voltage, when we made to flow current through a low pressure area, then without any conducting material, we see the flow of current. And to confirm this, what we did? So to confirm this, Faraday modified the previous experiment. The modification was that cathode was kept as it is, but your anode was filled with holes. So instead of taking a solid anode, we are taking a, a porous anode, okay, which is having holes through it. And this hole is shown with the help of dashed wedge. So this space between these red lines indicates that, okay, there is a anode, but it is having hole in between. Got it? Now, whatever be the source of this electricity, it would start from this cathode, move through the vacuum and hit this anode. Then after hitting this anode, the anode will accept that electron and the current will flow. But we don't know what was that particle which was carrying the current through vacuum. So after making a hole between these anodes, the particle will move through this gaps and will hit the back of the tube here. So some of will hit the back of the tube and some will hit the anode. Okay. The particles which will hit the anode, they will flow through the circuit, and the particles which hit at the bottom side of the tube, they will be providing energy for this zinc sulfide. So I've already told you that this back of this tube is coated. Coated means it is being painted with this zinc sulfide. As simple as that. Now, this zinc sulfide has a very unique property that as soon as something with a kinetic energy strikes it, it starts to glow. Okay. So the same glowing which you see on roads. Okay. You must have seen on the road that there is a coating on the road that starts to glow in the night. Yes, similar to that. So as soon as this particle hit your zinc sulfide coating at the back, it starts to glow. Now this created a buzz that, okay, we have something that is flowing through this vacuum, hitting the anode, making the current flow, and that is being confirmed with this help of fluorescent coating that starts to glow as soon as the high voltage is supplied. So this is written as bright spot. Okay, I would say that don't go beyond this term. Just try to think of it as your thing that you see on the roads, right? That starts to glow in the night. Okay, just think of it in the same way. So phosphorant is a name given to a special type of group of material that starts to glow on hitting with some particles which have kinetic energy or which have energy. So a particle which is having energy must be hitting this bottom of the tube. Okay, so you must have seen this same thing on the trees also. So your tree, if you have moved through cars and buses, you must have seen that on both sides of the roads, your tree is painted with a special coating that is only glows at the night. Okay, so similar to that material, this is zinc sulfide. Okay, got it? So this was Faraday's experiment. Now moving on further, what we can say from the Faraday's experiment? The first thing is that there is rays. Okay, there are some rays which are moving from cathode towards the anode. Now those rays are called as cathode rays. So Faraday named them as cathode rays. Second thing, the rays which we are talking about, they are not visible, but this can be observed if we use materials like fluorescent or phosphorant. So these materials, on striking with or on getting hit with this cathode rays, starts to glow. Got it? So this same phenomena was used in the older version of the television for the screen thing. So they use the fluorescent and the phosphorant tube there also. Okay. Anyways. Now, what will happen in the absence of electric and magnetic field? These rays travel in a straight line. So in the diagram, you can see it very clearly in the previous diagram that it was starting from the cathode and moving straight to the anode. So they travel in a straight line until and unless we supply a electric field or a magnetic field. Now we will study about this thing, this point. You will get a more clear picture of this when we will study about the J.J. Thomson. So these are the three characteristics of cathode. Remember, they start from cathode and move towards the anode. Second thing, they are not visible until and unless they are identified with the help of fluorescent and phosphorant. And third thing, they move in a straight line. And we have seen all of this in the experiment. Got it? Any doubt in this thing? Now, the fourth result was that if we supply any electrical or magnetic field, then these cathode rays behave like a stream of negatively charged particle. So we will see what will happen on applying electric and magnetic field. But there you will see that these observations are clearly indicating. We will see in the later slide. So we will see that the observation will clearly indicate that your cathode rays are negatively charged. And we named them the particle as electrons. So electrons were present in that stream which were flowing through the vacuum. So what is happening in that region? We know that we have gas molecules that are present in between the low pressure. Okay. Now when we supply high voltage, these gaseous molecules, they release electron upon ionization. So they get ionized. Ionize means to move electron. So when we supply very high voltage, with the application of this high energy, we abstract electron from the molecules. And these electrons, they act like a stream of particles which are called as cathode rays, and they move from cathode to anode, and they are responsible for the flow of current. So why do they behave like electron? Because they are electrons. Okay, because they are electrons. These cathode rays are electrons. Now, very, very important thing. So this point is very, very important, that the characteristic of cathode rays is not dependent upon the material of the electrode and on the gas that is present in the cathode ray tube. So we know that in the vacuum tube, we have gas that is present. But irrespective of the gas that we take inside the cathode ray tube, the particle has the same nature. Okay, so taking nitrogen, oxygen has no effect on the cathode rays or the stream of negative charges. So why they release these electrons? So see, the electrons are bounded to the center or to the nucleus due to the electrostatic force of attraction, because negative and positive charge attract each other, right? So if you take a gaseous molecule, it must have electron, it must have proton. In between they have the proton, and around it we have the electron, and they are attracting each other, or they are stick to each other because of the electrostatic interaction, or because of the electrostatic force. We know that positive and negative charge attract each other. But as soon as we supply a high voltage, so means we are supplying a high energy to that molecule. In response to that high energy, the electrons are plugged out. So you can think it's similar to the plugging of the fruit. So you apply force on the fruit, then it is detached from the plant. Here we are applying force in the terms of electrical energy, and that force is plucking out the electrons from the atom. Got it? Or the gaseous molecules that are present. Is it clear? Okay. So if we are saying that on changing the gas, if we are changing the gas, we are not seeing any change in that cathode rays. So the cathode ray is not showing any change in its property. It is independent of the gas that we are taking. It means that electrons are basic constituents of all the elements, and it is present in all the elements. So cathode ray is independent of electron. I have written it. Cathode rays do not depend upon electron, do not depend upon the material of electrode and on the nature of gas of present. So they are independent of both. Now let me try to explain it in a much more better way. So this was our cathode ray tube, and we said that we have a gas that is trapped inside it, and it is at a low pressure. It is at a low pressure. Now these gases must be present in the form of molecules. When we supply high voltage, these molecules eject electron. The similar analogy I've given you about plugging of the fruit. So this high voltage that is being supplied here is responsible for the plugging of electrons from the molecules. Now as these electrons are plugged out, since this is a negatively charged one and this is a positively charged one due to the supply of current, so these electrons which are negatively charged, they will repel from this electrode and they will move towards this electron, which is your anode. Got it? Is it clear to all of you? Now when we have multiple number of molecules, there will be multiple number of electrons which will be moving like this due to the electric field gradient or this cathode and anode ray presence, cathode and anode electrode present. Got it? So all the gases, they get ionized. Ionization means removal of electron from them, and they move from the cathode to anode. And that is the reason we are seeing the flow of current. Any doubt till this point? Now, moving on further, next is the J.J. Thomson's setup to calculate the charge to mass ratio. Now, what is the meaning of this? What is this charge to mass ratio? Let us try to understand this thing. So J.J. Thomson in 1897, he took the same cathode ray tube which was taken by the Faraday, and he started applying electric and magnetic field to it. And he applied them perpendicular. So if electrons or protons are attracted to each other, they are not sticked to each other because of a very strange force, which is nuclear forces, which is present between them. So this nuclear forces have a very unique property, that they are not operable at a large distance, but when they come close to each other, they repel each other. So at a very low, at a very small distance, these nuclear forces come into action and they don't allow electron and proton to get stick to each other. Got it? Now two things are there. When only electric field is applied, the electrons deviate from their path and hit at the point A. So this is your J.J. Thomson experiment. So he has taken that same cathode ray tube but with some modification. What was that modification? So try to understand this modification. This is very important to understand. So two things he did. This is your normal circuit. Okay, very good. Now in the anode, you can see that a small hole is there. Okay. So he took the same setup. All things are same except this right side part. So he added this right side part, and in this right side part, he has several things. First is the hole in the anode. So you can see that there is a hole through which that stream of particles are passing. So this red line is not visible actually, but it is shown to make you observe clearly. So this is the stream of particle that is traveling. Inside this flask, there are two types of field that are applied. First is this electric field. So again, we have a negative charge here, a negative charged electrode here, and a positively charged electrode here. Okay. So you know that your electron is negatively charged. If it is negatively charged, what will happen? It will move away from the negative electrode, which is this, and move towards the positive electrode, which is this. Therefore, instead of hitting and traveling through the straight line and hitting this point B, it has started to hit on point A. Any doubt in this? Just first try to imagine this setup. Okay. So we have taken the same setup, but we have applied two fields, magnetic field and electric field. First, I am talking about electric field. Is the concept behind the deviation clear? So in the normal case, what would happen? So J.J. Thomson applied perpendicular electric and magnetic field. So this is the electric field, this is the magnetic field, and this is your direction of the flow of this electron. Okay, and all these are mutually perpendicular. Got it? Now, this electrode which is present on the downside, which is yellow in color, it is having a negative charge. And this one is having a positive charge. So as your particle, which is electron, it will move through this hole. They will get attracted towards the positive charge, and hence it will hit at this point A. So this is a deviation. It goes like this, it goes like this, and it starts to deviate because of the positive charge. If it was not present, then it would have moved through a straight line and hit at this point B. Now, what about magnetic field? So, anyone has any doubt in this electric field part? Then I will move to the magnetic field. Okay. So, let us move to the magnetic field now. So, you can think of this gray material as magnet, where this is the south pole and this is the north pole. Navreet, this is your magnetic field. Okay. So, of course, magnetic field are the lines which are created, which move from the north and move towards south. Start from the north and move towards south. Now, moving on to this. So, this is your magnetic field now. So, first what we did, we took the whole Faraday's experiment. Okay. Now, first we applied electric field. So, it hit at point A. Now, in the second part, we are applying this magnetic field. Okay. So, Navreet, in the previous slide, I have assumed that the magnet is not there. Okay. I have only assumed that we have a electric field present. Got it? Now, in this point, I am assuming that we have only the magnet that is present and this electrode is not working. So, in the diagram, both are shown at a time. But here, so these are the 3 points. Okay, so they are the point where the electron is striking. When we apply our electric field, so since your electron is negatively charged, therefore, the electrons is moving towards point A because it is positive and this one is negative. Now, why it is moving toward point C on applying the magnetic field? This thing is important. So, you have to use the flaming left hand rule. Okay, just go and see about it. So, whenever a charged particle is moving, say in a magnetic field, there is a force that is applied onto it, and due to that force, what will happen? The electron will hit the point C. So they are not inclining to any part. I've already told you. So suppose this is your direction of magnetic field. Okay, so it must be going like this, north to south. So it is not deviating towards south. So this is a 3D figure, right? This is a 3D figure. If suppose your direction of magnetic field goes like this, okay, then your electron goes and hit on this side, on the downside, okay, on the downside, not towards the south pole or towards the north pole. It is going on the downside. Are you able to say analyze this thing or imagine this thing? So I have repeated it, yes. So these are the 3 points, Navreet. Listen it very carefully. That upon not applying any field, nor the electric field, neither the magnetic field, the electrons will go and straight hit at the point B. So this is your B that we are talking about. Okay. Now, when we apply an electric field, which is having a positive charge here and a negative charge here, the electron will move. Since it is negatively charged, the electron is negatively charged, it will move towards the positive part. So therefore, it will go here and hit the point A. And if we apply the magnetic field only magnetic field, and switch off this electric field, then due to the flaming head, due to the movement of charged particle in a magnetic field, it will hit the point C. You can just find this thing with the help of the flaming left hand rule. Is it clear, Navreet? Anyone has any doubt till this point? So your task would be just go and try to apply the flaming left hand rule to this. Okay, and try to find out that which is the direction of flow of the direction of the movement of the charge. Just remember that if your electron is flowing in left to right, then your current will flow from right to left. So you will take the direction of current in this direction. The magnetic field will be here. So red line is showing that it is the trajectory of the electron. Okay, it is showing the trajectory of the electron. Now, let us move further and see that what was the argument about the deviation of the particle from their path. So why are these particles deviating from their real path and not hitting the point B? First thing was, if we apply a greater magnitude of negative charge on the particle, so if we apply a greater potential, perpendicular potential, then the deflection will be more. Okay, so of course, if there is a more, electrodes are present at a greater potential, there will be more deflection. Okay, this is the first point. So it is very obvious. So more charge on the electrode means more force of attraction, therefore more deviation. Second thing was that the mass of the particle is the second point. So lighter is the particle, greater is the deflection. What is the third point? So third point is the strength of the magnetic field. So if you apply greater electrical or magnetic field, the original path will be excluded in a much more greater way. Got it? Any doubt in these 3 points? Now moving on to the determination of E by M ratio. So what is this E by M ratio? So what Thomson did, that instead of applying electric field and magnetic field individually, he applied both of them at the same time. Means he applied the electric field and magnetic field simultaneously. Okay, and he tried to balance the trajectory of electron. Okay, it tried to balance the trajectory of electron by applying a proportionate amount of electric and magnetic field. So it is very obvious now. If the particle is lighter, then it will deviate more. So if you are hitting if you have a heavy ball, then you can say deflect it less. If you have a lighter ball, then its path can be deviated more. Okay, so because more force, a little force can easily deviate that part. Yeah, it is the inertia that is due to the mass of the particle. Now, we will not go on how he determined this E by M ratio. You have to only think that he did one thing. Okay, he applied a very proportionate amount of electric and magnetic field simultaneously, so that there is no deflection and it hit the point B, which was the original path. Okay, and on the basis of this, and some behind calculation is also involved in it, he calculated this E by ME ratio. Now, throughout this lecture, some points are important, I would say, not all the points. So, if you are understanding those points, it's very good. First thing, what are the characteristics of cathode ray particle? So, the characteristics are, it starts from the cathode, hit the anode. Second thing is that it is independent upon the gas or the electrode we are taking. All of the stream of particles will have the same characteristic, and it will not depend upon the characteristic of the electrode or the gas that we have taken. Second important point. So these 2 points are important. Third point, they have a kinetic energy, and due to this kinetic energy, we are able to see a glow or a bright spot. Got it? First thing was this. Second thing, you must understand that why there is a deviation. Okay, so it's very obvious. Since it is a charged particle, so a charged particle will always move towards the positive electron. As a result of that, it was hitting a different point. If I was not applying any force, it was hitting its original path, which is coming in a straight line. Third part, if we apply magnetic field, so deviation means movement from its original path. Okay, suppose something is going like this. Now we have applied force. Instead of going straight, it deviates like this. So this is called as deviation. Got it? So as soon as we applied the magnetic field, there is a deviation of the electron from its mean path. Now upon doing some calculation and applying electric field and magnetic field both at some proportionate amount, he calculated the E by ME ratio. Where ME is what? ME is the mass of the electron in kgs and E is the charge on the electron. So this value come out to be 1.758820 into 10 to the power 11 coulomb per kg. Okay, C is the coulomb here. So charge will have a unit of coulomb. So C is coulomb and mass will have a unit of kg. So this is very important. This value, you must remember this. Now, next thing is the calculation of mass of electron. I am not going into the explanation of the the Millikan's experiment. So E by ME ratio is simply the ratio of the charge on the electron to the mass of the electron. E is the charge on the electron and ME is the mass of the electron. If you take the ratio, it will be called as E by ME ratio. Now, R.A. Millikan, with the help of an oil drop experiment, so you will see the description of this experiment in the book, but it is not there in the syllabus, so I'm not describing it. I'm only taking the result of it. So with the help of this experiment, he calculated the mass of electron. So we know the mass of electron, we know the ratio. Can we calculate the charge? Yes, very easy. You calculate the charge and it comes out to be minus 1.6 into 10 to the power minus 90. Okay. So we have the ratio of E by M, we have the mass, so we can calculate the charge. And the charge comes out to be 1.6 into 10 to the power minus 19 meter negative charge. Okay, you can see this calculation here. Now, if you put the mass of electron, if you put the charge of electron, then you can find the mass of electron as 9.1 into 10 to the power minus 31 kg. Okay, so there is a change. So R.A. Millikan found the charge on the electron, not the mass of the electron. He found the charge on the electron. If you put the value of charge here and divide it by the charge to mass ratio, you can get the mass of electron, because the E and E will get cancelled out. So we'll study about this Millikan experiment if we have time. Okay, so we will not move to this today. I guess there is a lot more to cover. So am I going slow in throughout this lecture? So this 1.6 into 10 to the power minus 19 coulomb, this is the charge of electron. So anyone who is facing difficulty with the pace of the lecture, then he or she can say it. Okay, so I'm going slow because this is a basic part, right? You have to get a hand of this. So the main points you should just try to grasp. So I have told you earlier, you must remember the characteristics of the cathode ray that I have given. And second thing, that deviation part. And third thing is the charge is to mass ratio. Okay. Again, you don't have to go into the R.A. Millikan experiment, but I will try to get it in the lecture if it is possible. So any doubt till now? So we have the mass of the electron, we have the charge on the electron, and we have the charges to mass ratio. Now, next thing, we will see the anode rays. So again, a modification with the cathode ray tube was done. So we did a small change in that, and this modification led to the discovery of the canal rays. So this was the experimental setup for anode rays. Now, what is the change that we have done? Students, we have not changed that much in the experiment. So the experiment is same. Okay, it is almost same. But what is happening in the reaction is something which we will discuss. So when we start to supply a very high voltage, initially the electrons are removed from the molecule. Okay, just listen it very clearly. Okay, so you will not see this diagram maybe in the book, but I have kept it here because a description of this is given here. So what I am saying is that when we apply a high voltage initially, the electrons are plugged out. Okay, yeah. So first the electron is plugged out. Once the electron is plugged out, the thing which is left in the, say, our nucleus was a positive charge particle. We know that our atom is electrically neutral. So that is for sure. If it was not so, then everything that is around you must carry a charge. But it is not so. That means our atom is somewhere electrically neutral. If there is a negative charge, there must be a corresponding positive charge to neutralize that. Got it? Okay. And this was discovered by applying further high voltage to that same gas or to that same experiment. So if we keep on applying this high voltage, the electrons will be first plugged out, and then a positively charged particle is being plugged out from it. Now, how do we make sure that there is a positive charge? In this case, rather than making holes in the anode, we have made holes in the cathode. You can see it. There is small gaps in between. Now, through this small gaps, again, this positive charge will travel and hit here, and this will create a glow at the end. And this indicated the anode rays. Okay, this indicated that something positively charged is present because it is moving towards the anode, which is negatively charged, and is creating a glow at the end of the tube. In this way, we found the anode. So this glow, glow can be made to various particles. They can be phosphorant particle or fluorescence particle. They are responsible for this thing, like the previous one in which we have taken the zinc sulfide. Now, why is that happening? So that is a very vast thing to discuss now. So there is a molecular transition inside it. I will not go on to that. So what you can think of it is simply that if you are applying energy onto that phosphorant particle, then its electrons are being excited, and when they get de-excited, they release energy in the form of light. As simple as that. Okay. So in these materials, the electrons are excited easily due to this positive charge, and it is going to a higher excited state. Then it comes back and release energy. Okay, so I said it earlier, so we will not discuss much about it. So there is a lot more to discuss on it. Okay. Clear? Till this point, anyone has any doubt? So perforated disc tube means something which has holes in it. Okay, you can see that it is not continuous. There are holes inside between it, whereas the anode is a continuous strap. So this gaps between the dashed wedge indicate that they are having holes. So we are calling it as perforated. Now, what are the characteristics of this charged particle? First is, it is not moving from negative to positive. It is moving from the positively charged anode to the negatively charged cathode. Got it? So again, I am saying it. So perforated means something which is having hole. Okay. Now, what is the meaning of this? If the flow is opposite, means the charge is also opposite, because it is moving from a positive charge towards a negative charge, or it is getting attracted towards the negative charge, means it is having a positive charge onto it. Second thing, which is most important, in case of your electron, the charge is to mass ratio, or the characteristic of the cathode ray, was not dependent upon the gas that we are taking. I've said it earlier. Okay. But this thing is not true for the anode ray. Okay. So it depends upon the gas. Now, what is the meaning of gaseous ions? So gaseous ions are those gaseous molecules which are having positive charge on it. Okay. So after removing the electron, what is left? Atom is left which is having a positive charge onto it. So this positively charged gaseous ions, they are moving towards the negatively charged cathode, and its properties are dependent on the nature of the gas. Okay. Now, some of the positively charged particles carry a multiple of fundamental unit of electrical charge. So why it is carrying a multiple number of charges? Because from the same gaseous atom, we have removed multiple electrons. So if it is having more than one unit positive charge, and as a result, it is having a multiple fundamental unit of charge. Now its behavior is just opposite as compared to the cathode ray. So we can say that the smallest, lightest positive ion that was obtained from the hydrogen was called as proton. And this positively charge was characterized in the 1990. Now, what is the meaning of this? Whenever we take a hydrogen atom, it will have one electron and one neutron. When we take out one electron from it, what is left? So one electron and one proton. No neutron is present in hydrogen. So what is left in it? Only proton. Okay. So when this electrical discharge was done for the hydrogen, its electron was removed, and the only thing that was left was the proton. And this was discovered in 1919. But it may be not true for other gases, because suppose if we are taking helium gas, it has 2 protons. Okay, it has 2 protons. Upon removing of this 2 electron, this will have a different property which has 1 proton. Similarly, if you are taking a lithium gas, thing, then upon removing the lithium electrons, we will get 3 protons. Therefore, the characteristics of each of the gas was different. Got it? Now moving on to the last point, which is neutron. So this was seen that although summing up the mass of electron and proton, the mass of the atom was not satisfied. Okay. So there must be a third particle which is responsible for that mass, and we named that neutral particle as the neutron. This was discovered by Chadwick in 1932 by bombarding a sheet of beryllium with the alpha particle. We will study about this bombarding experiment also. And it was also seen that this neutron have a mass which is greater than that of the proton. And he named that particle as neutrons. This is a table for you to understand all of this that we have studied. So this is the charge that is present. If you calculate the relative charge, then it will be -1, +1 and 0. Similarly, mass will be 0, 1 and 1. For electron, we take the mass as 0, means relative mass as 0. For proton, we take it as 1. For neutron, we take it as 1. So if I have, so we will see this thing once again in the next lecture, since we are lacking time. So this was all for today's lecture. Thank you.